Hey everyone, so in the last lecture we started our discussion on hashing. In this one, we will cover specifically hash functions. So we'll start with what is a good hash function, what are the characteristics of a good hash function, and then what are the various hash functions which are very widely used in terms of this key and its slot mapping to identify what should be the slot given a specific key. So let's get started. So first, before jumping upon the hash functions, what a good hash function is? What are the characteristics of a good hash function? Or what, like if a hash function is given, how can you tell it whether it's a good or a bad hash function? So majorly, a good hash function has four major characteristics. The first is it should be deterministic. First, and like all four are important, but the first is it should be deterministic. What does it mean? It means that given an input, it should always give me the same output. It should always give me the same output, or else it won't, like we can't call it a function otherwise, right? So hash function should be deterministic, right? For instance, two keys k1 and k2 such that k1 is not equal to k2. K1 is not equal to k2. So for every time if I am passing k1 to this hash function, it should always give me h of k1. It should always give me h of k1, right? No matter at what time I am calculating its value. And same holds for any other key. For k2, the same function should always give me h of k2. And this should always be equal to no matter when I am trying to find its value. So this is what deterministic means. With time, it should not change, right? All right. So the second is it should be fast to compute. It shouldn't be the case that if I am trying to find a slot for a specific key for either insertion or searching or deletion, computing the hash value should not be the bottleneck for me. Computing the hash value should not be the bottleneck. So it should be fast to compute. Generally, a constant time hash function is a good hash function, right? Third, it should minimize the collisions. We already know what exactly a collision is. Given two different keys, if h of k1 is equal to h of k2, in that case both the keys are mapped with a same slot. Both the keys are mapped with the same slot. This is what collision is. Two different keys are mapped with a same slot. This is what collision is. So they will collide. So hash function should be defined in such a way that the collision can be minimized. If a specific hash function is minimizing the collisions, then it can be treated as a good hash function, or it is a characteristic of a good hash function, right? So collisions, and like one more important thing, you can't eliminate collisions. But they can be reduced, they can be minimized. So good hash function reduces their frequency. That's it. Okay. And the fourth in the list is uniform distribution. And like I am talking about the distribution of slots with the keys. It should have the uniform distribution in giving me the slots based on the keys I have in the universal set, right? So the keys should be distributed uniformly. And point number 3, the third characteristic and the fourth characteristics are related to each other. If the hash function is ensuring uniform distribution, that is another way of saying that the collisions are minimized. That's why the distribution is uniform, and we are not ending up in a situation where we have these clusters. Cluster is basically too many slots are allocated to different keys which are close to each other, right? So uniform distribution will always ensure that the collisions are minimized, or vice versa, right? So it says keys should be spread evenly across available indices or the slots. Okay, so these are the 4 characteristics which, if holds, then the hash function is a good hash function. All right. Okay, so let's start with the discussion of hash functions. So the first in the list is division method. First in the list is division method. We have already seen it, and we have also seen few problems on this division method hash function along with chaining in the last lecture. So I will be quick in discussing this method. So this is a very simple method, very easy to use, or I can also say it is one of the simplest hash functions. Okay, so it says give me a key. The function is k mod m. K mod m, mod is the remainder. Okay, k modulus m. M is the count of the total number of slots available to us, right? If we have m slots, if we have m slots 0, 1, 2 till m minus 2 and m minus 1, this is hash table. This is the hash function, which is m k mod m, right? So you pass the key, it will calculate, and based on the calculated value, it will allocate a slot from 0 to m minus 1, from 0 to m minus 1. And so on, right? So like it is not that difficult, it is just calculating the modulus remainder by m. Okay, so where key is mapped into one of the m slots, right? So based on the 4 properties that we discussed in the last slide, which is deterministic, fast to compute, minimize collision, and uniform distribution. Based on these 4 properties, let's discuss one by one. Can I say that this hash function is deterministic? Can I say that division method is deterministic? It is, yes, it is deterministic. So is it deterministic? The answer is yes, it is deterministic. Given a specific key, you pass the key, a specific key to this hash function, anytime it will always give you the same slot. For instance, k is 3 and m is 10. In that case, h of k, no matter when you are calculating this h of k, if it is defined by the division method, it will always give you 3. It will always give you 3. So yes, it is deterministic. Is it fast to compute? The answer is yes. We are just simply calculating the modulus operation. We are just having the modulus operation. So it is fast to compute. But the next 2 points, is it helpful in minimizing the collision and ensuring uniform distribution? The answer is no. It is easy to compute, it is fast, it is deterministic, but it is not very good hash function when it comes to minimizing the collisions. That's what the bottleneck of division method is. There is a trade-off between easy implementation, faster calculation, and the collisions. Okay, so there are some pitfalls when it comes to division method. If you choose m in such a way that it is power of 2, if it is power of 2, then the number of collision will increase. For instance, if let's say m is 2 to the power 3, in that case you pass k, the key, as 8, it will collide with 16, it will collide with 24, and so on. So generally the m, to ensure or to reduce the collision frequency, m is chosen in such a way that it should be a prime number, which should not be close to the any multiple of 2. For instance, 701 is a good m. This is a good m. So in general, the overall idea behind this is, it is easy to compute, it is fast, but it is not ensuring minimal collisions. But even if we want to use it, we choose m in such a way that it should be a prime number and should not be close to any multiple of 2 or a power of 2, right? Okay, so a prime m is preferred. So second in the list is multiplication method. So let me add one more point in the characteristics of a good hash function. So if I discuss this uniform distribution, if I say this uniform distribution, can I say this? If somehow I introduce a characteristic of randomness, if somehow I introduce the random characteristic in calculating, while calculating the hash value, will it be uniform? Can I say that if the hash function has randomized my allocation of keys, ensuring the deterministic characteristic, if I somehow introduced some sort of randomness, will it help me in giving a uniform distribution? The answer is yes, it will. It will give me a better uniform distribution compared to a non-random static hash function, which is my division method. Straight away give me m, take modulus, and give me k, take modulus with m and get the slot. It is pretty straightforward. So there is no randomness, which is why it is not collision free. There are it is prone to collision. So therefore somehow introducing some sort of randomness will always ensure my uniform distribution. Of slots, right? And now there are different ways to introduce this form of randomness. There are different ways. The first way is by applying or the calculating the hash value by this multiplication method. Calculating the hash value by multiplication method. So what it is a two-step process. So later I will explain you how we have introduced some sort of a randomness in order to get my slots value, right? So it's a two-step process. So there are two different ways. The first one, I have simplified it just to give you the explanation. The second is a bit more complex way, which generally is used when it comes to calculating the hash value by this multiplication method for systems or computers. This method involves bytes, right? But both are same. This is the simplified version to understand how exactly we will be calculating the hash value, right? So it's a two-step process. This method is a two-step process. Step number one, the idea remains the same. We have key, we will pass it to a box h, it will give me the hash value, it will give me h of k. This will be my slot, right, or the index of the slot in the hash table. So the first step is to multiply the key. We have the key, multiply the key by a constant, and the constant should be from 0 to 1. The constant should be from 0 to 1. Okay, so this is step number 1. After multiplying, we'll take the fractional part of k times a. For instance, if k times a is 24.179, in that case we are only considering this fractional part. Okay, we just ignore the integer part, we will only consider the fractional part. This is step number 1. You take k, you take the key, multiply it with a constant, and only take the fractional part. Correct? Step number 2. Now multiply that fractional part by m. M is total number of slots. Multiply it by m and then take the floor. Okay? So this is what your hash value will be. And in this k times a mod 1, this is another way of saying that only consider the fractional part, which is if you want to calculate the fractional part of any number, take the modulus by 1. So x times x of mod by 1 is equivalent of x minus integral part of x. This is same. It is same. It will, if x is say this, it will give you 0.179. It will give you 0.179, right? You take that fractional part and multiply it with m. This is my fractional part. This is my fractional part. And multiply it by m. After multiplying by m, you just take the floor. You just take the floor or the integral part of that final multiplied value of m times the fractional part of k and a. Okay, so this will give you the hash value. This will give you the hash value, and this is another way of representing this only. We'll see this method as well, and we'll see that the answer remains the same. Okay, so intuitively, if we try to think of this method, what exactly the multiplication method is doing, which is, think of it as a stretch and chopping method. Stretch and chopping method. You have k. First we are stretching k to ensure that it should lie between 0 and 1. K times a spreads the keys. So we can have multiple keys, right? We can have hundreds or thousands of keys. So what we are doing, we are spreading the key across the interval 0 to 1 by multiplying it with a, right? We are spreading the keys such that the keys should lie from 0 to 1. Then we are multiplying it by m. Okay, the first part is spreading it in the interval from 0 to 1 is another way of saying it. We are only considering the fractional part of ka. Fractional part of ka. Okay, and this is what the element of randomness is. No matter what key you are taking, you are converting it into some another form, which is k times a, and only considering the fractional part. Okay, so the initial key is completely modified. So the initial key that we have started with, for which we need to find the slot, is completely modified. Okay, the second step is like multiplying by m, which scales that interval to 0 to m. Ultimately, we want to find a number from 0 to m such that we can map a specific key with the slot. So this will give us a value from 0 to m minus 1. Okay, and then taking the floor picks an integer slot in 0 to m minus 1. Okay, so this is the overall idea of stretching and then chopping. Like, it is some sort of a way in which we have introduced a randomness while calculating the hash value from this multiplication method. Okay, and this is a way, and similarly we have multiple ways. We'll see few more later. Okay, so now let's have a problem. So in this problem we have to calculate the hash value given the value of the key is 20 using the multiplication method that we just discussed. So let's see what are the parameters that are given to us. Initially, key is given, which is 20. Then the table size, or m, is the key. The hash table have 16 slots, 0 to 15. Okay, so 20 will be mapped in 0 to 15, right? Then you have word size. So you can ignore this word size for now, because this is for the another method of calculating the same hash value using this, right? And finally, a constant is given. Okay, so let's see how we can calculate it. So we'll start with step number 1. Step number 1 is to calculate the value of multiplier k times a. Okay, multiply k with a. So k times a, what will it give? 20 times 0.63. It's 20 times 0.63. So 6, 12, 12.6. It will be 12.6. Okay. So once we have this multiplier, we will extract its fractional part. Extract its fractional part. Okay. So it will give us 0.6. This is our step number 1. Once we have the fractional part of k times a, we will multiply it with m and then take the floor. So m times fractional part of a. This is k a mod 1, right? So m times k a mod 1, what will be? It will be m is minus 16, m is 16, 16 times 0.6, 16 times 0.6, 9.6. It will be 9.6. So therefore hk will be floor of this. Hk will be floor of m times k mod 1, which is floor of 9.6 or the integral part of 9.6. So it will give me 9. It will give me 9. So the hash value of 20. So key 20 will be mapped with 9th slot. Okay. So in this step, in step number 1, this 0.6 is what the randomness is. This is randomness. We have somehow mapped 20 with 0.6. We have somehow mapped 20 with 0.6. Okay. And the another method, which is not another method, this is the same way. What it says, it is saying we are doing exactly the same thing. Let me explain it to you how. So we have this k, right? For instance, k times a was 24.179, right? So what we are doing is, rather than dealing integral and fractional part separately, we have upscaled our constant and multiplied with 2 to the power m. We have upscaled the constant. The constant is from 0 to 1, right? We have upscaled it by converting it, by multiplying it with 2 to the power w, which will give me a w bit number. This will be w bits. Yes or no? So k is my w bit initially, and a times 2 to the power w is also a w bit number. So the resultant of the multiplier of k times s, the resultant of the multiplier of k times s would be a 2w bit number. This will be 2w bits. These will be w, which is r1, and another w bits r0, right? In such a way that the most significant w bits, which is r1, is the integral part of k, of ks, like, or k, it is the same thing, of ka, integral part of ka, and the least significant w bits will be the fractional part of ka. This will be the fractional part. This will be the fractional part of ka, right? And then the next step is to extract the most significant p bits out of the least significant w bits of r1 r0, or the initial multiplier that we got. Okay, so extracting p bits is same as multiplying it with m and taking the floor. This is exactly same as, why? Because p is 4, which is log of m, So this is extracting p bits, same as multiply by M and take floor, right? So this is another way of calculating the hash value, in which we are not dealing the numbers in fraction. Okay, we are just upscaling the constant in such a way that it is no longer from 0 to 1, it is a w bit number, and then multiplying it with k and ignoring the fraction, ignoring the integral part, which is the most significant w bits, and then only considering the this R naught, which is the LSB, least significant w bits of multiplier k times s, is what the fractional part of step number 1 is. This is what R naught is, and then extracting p bits, which is multiplying by m and taking floor. So it is same, but like for understanding, go with this method. To solve the problem, go with this method. Both will give you the same answer. This is like the second one is like manipulating the bits so that we do not have to deal in fractions, right? But this is the overall idea. We introduce randomness, multiply it with a, and then get the hash value. Now the question is it deterministic? Is it deterministic? The answer is yes, if a is constant for all the keys. If a is fixed, then it is deterministic, but like if you are keep on changing a, in that case it won't be deterministic. So to ensure the deterministic behavior, you have to take a fixed value of a, like choose a and then go with that for all the hash value calculation. So deterministic for fixed a, it will be deterministic for a fixed a. Correct? So choosing a constant would be a challenging process when it comes to, we have to choose a in such a way that the distribution, which is the degree of randomness that this a is bringing in this algorithm or the method, should ensure the uniform distribution. Okay, and like experiments have shown that choosing a irrational number, square root of 5 minus 1 by 2, works pretty well. This works pretty well. Okay, and like I forgot the mathematician who gave this constant, but like a, if you choose a, it will like do really well when it comes to distributing the keys with a slot in a uniform manner. Okay, all right, so this is multiplication method. Now the pros and cons, like as I mentioned earlier, it is fast and simple. If a is fixed, calculating it won't be a difficult task, right? Multiply or by bit shifting mask, no division is involved generally, and it behaves okay. It behaves okay even when m is non-prime. Even if m is non-prime. In division method, if m is non-prime, it doesn't work really well. Why? Because there are too many factors that might encounter the collisions. Okay, that lead to collisions if there are too many factors of m. So generally in division m is taken as prime, but even if you take non-prime in multiplication method, it will work well. Why? Because you have introduced randomness by the way the multiplication method is designed. Okay, all right, so a good distribution, it is better than the division method. Multiplying with an irrational constant spreads the key uniformly. Multiply it with an irrational constant, generally do a uniform distribution or the spread of the keys. But there are certain disadvantages, which is the quality of the distribution. The quality of the distribution is very dependent on what the value of a you should choose. It hinges on a. So quality strongly depends on a. Quality of distribution, how good or how uniformly the distribution is of key to slot, will depend on a, right? And second, like this is not that much significant con, but it is not cryptographically strong. which is if you have key, you can easily identify what should be the slot. So yeah, this is not cryptographically strong, okay? But the overall conclusion is it is better than the division method. Multiplication hashing is fine for speeding up ordinary hash tables, but it offers no formal collision restraints or like a resistance or security guarantees if someone is trying to break it. It is breakable. If you have you have break the mapping of key to the slot, right? So from security perspective, this is not that great, but when you compare it with the division method, it like works quite well, right? So let's see the next one. Next in the list, which is like the best out of what we have discussed till now, is universal hashing. This is universal hashing. So what it is, let's see. So rather than using a single hash function, we have something called a set. We have a set of hash function, where we have multiple hash functions, say h1, h2, h3, and so on. This is what capital H is, a set having multiple hash functions. We have all possible keys, the universe of keys. It is similar to the other hashing techniques as well. We have multiple keys. Then we have number of slots. We have fixed number of slots in the hash table, and we have to find a way to map a key with a slot. The only difference is, rather than having a single hash function, we have a set of hash functions. And the idea is to pick a hash function. At random. So we randomly choose one hash function and then start our mapping, from key to the slots. Okay, when the program starts from a set of functions. Okay, so this is what universal hashing is. It is saying that I am not restricted to a single hash function. I have a bunch of hash functions, and out of which, before starting my hashing, before the program starts, I am randomly choosing any one of them and then mapping the key to the slot, right? So the theorem says H is universal. When can you say that this set is universal? There is a condition which says for every two different keys, small k and small l, present in U. So there are two keys, k and l, present in this set of all possible keys. So the chance that h of k is equal to h of l, this is small h. The chance that a randomly chosen hash function from the set of all hash functions, a randomly chosen hash function from capital H, from the set of all hash functions, if small h of k is equal to small h of l, if there is a collision between two randomly chosen key from the set of all possible keys using the randomly chosen hash function from the set of all hash function, is at max, should be at max or at most 1 by m. If this holds, in that case, the capital set H, which is the set of all hash function, can be called as a universal hash. Okay, so this is a basic condition that no matter which hash function you are choosing, like the intuitive idea behind this theorem is, if you randomly choose two different hash functions and if you randomly choose a specific hash function and apply it on two different keys, so the probability of the collision should be at max 1 by m. If it is exceeding 1 by m, in that case, the set of all hash function is not universal or not that great. Okay, it is not giving you uniform distribution, or it is not helping you in that way such that the number of collisions can be minimized, right? So this is what a universal hashing is. Now the question comes up, like how to define this set, how to define capital H such that you have multiple hash functions in the set. So let's see. We will only discuss one method in this, which is also known as Carter-Wegman method or mod prime method. The idea is to build a universal family. What it means? It means the idea is the building universal family is what? Creating capital H, or creating capital H, or a universal set of hash functions. Okay, so this is like, there are multiple ways, but we will be only discussing one, which is mod prime, or like widely used as well. Okay, so we'll start with pick a prime number p. Pick a prime number p larger than any possible key. So if you have m keys, choose a p such that it is larger than total number of slots available in the hash table. So p should be prime. And it should be greater than m. Okay. Once you chose p, then randomly choose two numbers. Small a and small b, a and b. Randomly choose two numbers, a and b. Randomly choose two numbers, a and b, such that a should be from 0 to p minus 1. A should be from p minus 1 and b should be from 0 to p minus 1. Okay, so a and b should be lesser than p, but a can't be 0, b can be. And then finally the hash function would look like this. This is a times the key plus b mod of p, and finally whatever the value you are getting, take mod by m. This will give you the hash function. And now by tweaking or changing, now for different values of small a, small b and p. So a and b are depending upon p. By different values of a, b and p, you can form the entire set. We can form the entire set of hash functions. This is what we will call capital H. Right? So we have a technique, this is called as mod prime technique, to get a universal hash function H. Correct? For instance, let's assume you are taking p as 17. It's a example. P as 17. You can take a as say 3, b as 5, and your m was say 25. Right? For this specific configuration, you get a hash function, your h of k. You get a hash function. What it will be? A times k, which is 3 times k, 3k plus b, which is 5, mod with p mod 17, whole mod m mod 25. Okay, so this will be your hash function. This is a specific hash function h1 chosen from a set of universal hash. This is h1, a specific hash function for a certain configuration of a, b and p. You can change a, b and p to choose some another hash function, right? h2, h3, h4 and so on. It will lie, h1 will lie in capital H. Again, change the value of p or take the fixed value of p. Even just changing a and b, choose a different combination of a and b will give you h2, h3 and so on. Then you can have like infinite hashes, like many hash functions just in the universal hash. Okay. All right. So this is what the Carter-Wigman or the mod prime method is. And if you have the hash function, getting the slot value from the key is not that difficult. You just pass the value of key. In this instance, you just pass the value of k and get the value, right? For instance, let me calculate. If k is say 5, if k is 5, in that case h1 of 5, what it will be? It will be 5 times 3 times 5, 15 plus 5, 20 mod 17 will be 3. It will be 3 mod 25, it will be 3. So getting or calculating the slot is not difficult once you have the hash function. Okay. All right. So now the important thing, same as the multiplication method, fixing in the multiplication method, we are multiplying it with a constant a, which is from 0 to 1. And once the constant is fixed, the method is deterministic. The technique or the hashing is deterministic. Same holds for mod prime as well, which is the Carter-Wigman method or Carter-Wigman hashing is deterministic. The Carter-Wigman method is deterministic during runs given the chosen random parameters. What it means? The random parameters, which is a, b and p, are fixed, or after choosing we have fixed these parameters, then only this hashing is deterministic. Else the randomized, it will be randomized across runs if we resample these parameters. If we resample these parameters, and resampling these parameter means choosing different a, b and p. Choosing different a, b and p. Okay. So if we just change these parameters, you have entirely different hash function. So it won't be deterministic given a specific key, right? Okay. So let's see a problem. So universe of key is up to 20. We have 20 slots, 0 to 19, and no, the keys are up to 20. The keys are up to 20, but the slots are from 0 to 4. The slots are total 5, 0 to 4. At table creation, we randomly select. Okay, so we have a prime number, not a, p, which is fixed, and small a and small b as 7 and 3. So I'm writing h of k. For mod prime, it will be a times k plus b mod p mod m, out of which m is given as 5, p is given as 17, and a is given as 7, finally b is 3. So function turns out to be 7k plus 3 mod 17 mod 5. Okay, so this is your hash function. Once the hash function is fixed, like calculating slots given the keys. So use this Carter-Wigman universal hashing scheme to compute hash values for 3 different keys. Let's see them one by one. Okay. So case A, my key is 4. Starting with 4, h of 4. What it will be? It will be 4 times 7, which is 28 plus 3 mod 17 mod 5. So 28 plus 3 will be 31. 31 mod 17. 31 mod 17. 27. 4. It will be 14. 14 mod 5. Which is 4. Right? For B part, if k is say 10, h of 10, it will be 70 plus 3, 73 mod 17 mod 5. Okay, so it will be 17 times 3, 52, 17 times 4, 68. Yeah, 5 mod 5. It will be 5 mod 5, which is 0. It will be 0. Okay, and similarly we can compute for the third case, which is what if it's 15? What if it's 15? 15 times 7. It's calculations are involved. You can easily calculate and get the value, right? So this is how you will be using a universal hashing technique, specifically Carter-Wigman, in order to introduce some sort of randomness rather than just having a simple division method of calculating these slots. We can introduce some randomness using these techniques to ensure or to have a better uniformly distributed hash function, right? All right, so like I am restricting the discussion at this point. There are like multiple topics which are advanced topic, which are like out of scope of the GATE or the semester exam. So we are restricting the hash functions here, but there are, like, if you want, you can study resources where there are different, like, additional to mod prime, there are some other universal hashing techniques. Other universal hashing or hash functions. There are, along with it, we have only restricted the discussion which involves the keys to be numbers or specifically integers. There are hashes, there are hash functions which involves fractional keys or string keys. Keys can be string as well, right? But again, these topics are like miscellaneous or advanced and beyond the scope of the GATE. So we won't be discussing at this point of time. Hope you guys enjoyed this lecture. Like, see you in the next class.